All right, this is the lesson on rotations, and you'll notice, I don't know if you noticed this or not, but kind of last minute last week we decided to reverse the order of these because of where the quiz is and reviewing for the quiz and that kind of stuff. This lesson on rotations is actually a lot more to talk about than the one we originally had as the lesson on this day, which was translations. Anyway, doesn't really matter, just hopefully you're on the right one today. This is 9.3. Rotations. The other one is 9.2 translations. They're all on the quiz. So here we go. Rotations are another type of transformation we're going to learn about. Reflections is what we did previously, and rotations are just another one. Unfortunately, they both start with R, so we have a bit of a notation thing to think about in a second, but there's a way to get around it. All right. So a rotation is something that turns every point of a pre-image through a specified angle and direction about a fixed point called the center of rotation. Let me show you what that looks like. All right, so I've got one set up in Sketchpad here. This little pentagon thing I've got set up to rotate, and it's going to rotate around this. This is the center of that rotation, and then I've got a little thing down here I can use to control the angle. So watch, when I move this angle, it rotates this figure. So right now the angle looks like it's about 90 degrees. We could say this figure has been rotated 90 degrees around this center, and it started here. So the green thing has been rotated 90 degrees this direction, and it became the red thing. We can rotate any number of degrees, so this is about 180, this is about 45 or so. Of course, if you rotate 0, it doesn't do anything. If you rotate all the way around back to 360, it doesn't really go anywhere. So rotations are motions that kind of go like this. So notice how this center here, we call it the center of rotation. If you see what kind of path this thing is rotating in, I think maybe you can understand why we call this the center. It's like the sun in the universe, and we've got this thing that's orbiting it. If we move the center, we move kind of how the orbit looks. So now if that's the center, and the location of this angle, this is just an angle I'm using to control the angle of rotation. This has no location properties. Anyway, this center, if I move it to where it is now, notice the rotation is kind of a lot tighter. Now it just spins around that point. I could put the center of rotation kind of here, then we'll notice what happens. It rotates just kind of like this. I could put the center of rotation on one of the points, then the rotation kind of looks like this. All right, so what we're going to talk about today is how do we decide, what's the sort of geometric rule here about how this point rotated and went right here, and how this point rotated and went right there, kind of scientifically speaking. All right, and that's what's right here. So we need a center and we need an angle, and it's called the center of rotation and the angle of rotation. Rotation about point O through x degrees, so there's the center, there's the angle, is a transformation such that if a point P is different from O, so if we're talking about some point that's not the center, I could draw this down here. Let's say we were defining a rotation. And here's the center of rotation, O. I'm trying to make a point. That's point O. I'm just trying to make a point here. Yeah, okay. And there's point P. And we're going to rotate it. Let's say, I don't need to draw this degree. Let's just say, that's a sketchpad thing. Let's just going to say we're going to rotate through 45 degrees. So we're going to do point O, and we're going to rotate 45 degrees. Where does this point P go? Well, it goes, if it's a different point than O, it's kind of got an exciting life ahead of it. It's going to move somewhere. If it was actually the same point as point O, think about doing a rotation there. That point's just kind of going to twist on itself where it is. But if that's the center of the clock, and that's the point at which you're going to hold down the paper and spin it, it just kind of turns right on itself. It doesn't go anywhere. So if it is the point O, then that doesn't move. But if it's any other point, it does this. The distance from O has to stay the same, so it's going to go some other place that's just as far away from O. So in other words, it's going to stay on a circle. It's like there's a radius that's centered at O, and we draw it out to P. It's going to stay that same distance away from O, so it's going to be on. That's hard to wave my mouse in a circle here, but it's going to move along kind of an arc path, and it's going to move as far along that arc path so that the angle from P to O to the new point has to be whatever we said was the angle of rotation. So if this is supposed to be P prime, it's going to, what that means is, or how that was calculated was, these radius things had to be the same, and this had to be the angle of rotation. Now you might be thinking, well, why did I go 45 degrees that way? Why didn't I go 45 degrees this way? How come that's not P prime up here? why isn't it there? Well, we'll talk about that in a second, because 45 degrees, we could kind of go two different directions on that. Which one's correct? Well, I'll tell you, it's the purple one. And here's why. So that's not confusing, so that you don't know which way to go, or so that we do know which way to go. We define these angles in terms of positive and negative, kind of like numbers on a number line. Positive is defined to be, let me highlight this. Positive is defined to be counterclockwise. Counterclockwise is positive, and clockwise is negative. I think the people who invented clocks did not speak to the people who invented the coordinate plane, essentially. The reason why counterclockwise is positive has to do with your good old friends, the x and y coordinate plane. And there's a really good reason, and you'll figure this out more in Algebra 2. There's a really good reason. If that's the positive x-axis, and this is the positive y-axis, etc., the negative y's are down here, and the negative x's are over here. There's a really good reason why this direction is considered to be positive. And I think these people were right-handed, and the people who invented clocks were left-handed, and so they just didn't agree, and that's why we have clocks that don't agree with the coordinate plane. But that's the way life is. So counterclockwise is positive. You could have a couple different equivalent angles for same rotations. If you said you were going to rotate this point P 30 degrees, and this would be positive. If we're going from here to here, that's counterclockwise, so that's positive. If you were to rotate that point 390 degrees, it would go all the way around the circle once, and it would end up in the same place. We could add another 360 and call that 830 degrees or something. No, that's not right. 750 degrees, and it would be in the same place. Also, to get from here to here, you could also go around the circle that far, all the way around. That would be a negative 330 and end up there. So there's a lot of equivalent measures for the same thing. So I could have called this, 750 degrees is the same thing. I could have called this negative 690 degrees. It kind of would have been the same thing. So all of those rotations, 30, 750, 390, negative 690, negative 330, they all would do exactly the same thing as 30. So that's a bit confusing, but if you always the standard ones are the ones between negative 180 and positive 180. We kind of usually use those. You start using numbers bigger than that, they're fine, they're defined, but they're just kind of non-standard. They're not wrong, though. Oh, I didn't show you the notation. Here's the different R. It actually just means we're going to use a different font for the rotation font, R. There was the reflection font, R, and that was just a regular old R. That's for reflection. So that was from a couple of days ago, depending on what day you had class. Anyway, first lesson was reflection. This is rotation. And for rotation, you need to have two things specified and have like a little subscript with two things in it. With reflection, it was reflection and all we had was a line, right? All you needed to know was, that's the word line, what line to reflect over, and then all of a sudden everything in the whole plane, you know what to do because you know what line to reflect over. Here you need a little more information. You need a center. Ooh, can I draw this easily? We need a center, and you need an angle. And that's what this means. This is a reflection using point O as the center and negative 90 degrees as the angle. One other thing I thought about from this page, just a little blue sentence I didn't talk about. Rotation, just like reflections, rotations are another type of isometry, meaning if we were to rotate an entire triangle or if we were to rotate a fancy pentagon, what ends up happening is the rotated version of that pentagon, it's more fun if I move the center, this is in every way congruent to this. And we can establish that by simply saying any distance over here before is congruent to the distance after. If that's always the same for any 2 points you could possibly pick, you're going to end up with congruence all the time. And this is one of those things. So this is an isometry just like reflections. Oh, and I thought about something else here too. Remember how if the point was at the center, it doesn't go anywhere? That kind of reminds me of reflections. And reflections, if the point is on the mirror, it doesn't go anywhere. So we have the same kind of two-part description. All right, one special rotation is if the rotation is exactly 180 degrees. So if we rotate this thing exactly 180, make that a straight line, we kind of have this cool feature here. First of all, it's really hard to tell whether we went positive 180, which would be this way. This would be positive. Positive would be counterclockwise. Or did we go negative clockwise? We don't really know. So we could call that positive 180 or negative 180. It would end up in the same place. So there's one special feature of 180, but another special feature of 180 is what ends up happening if you think about the radius of from the center to the original point, then you flip that 180 and we have this new radius to the image point. Well, that's going to make a straight line. That's going to be collinear because we're going exactly 180 around. So performing this, like if you had in pre-image point R here, you measure straight to the center. You can just leave your ruler right there and keep going because 180 degrees is just straight. You just keep going in the same direction. You set it up so that O would have to be the midpoint of that to keep this radius the same and to make that 180. So that's got some special properties. It kind of feels like you're doing a reflection around a point. You measure to the point, you keep going the same direction just as far as where you came from. That feels like reflections, but we're going around a point now and we're not going perpendicular to anything. It's called a half turn, and it has a nice, if we're doing this in coordinates, it has a nice coordinate shortcut here. The point xy would become the point negative x, negative y. Put that in your list of coordinate stuff to remember. All right, so here's some actual problems. If O is supposed to be the center, we're going to rotate around point O in all of these. What if we rotated negative 90 degrees? So we're going to spin this whole figure negative 90 degrees, which is 90 degrees clockwise. Where does B end up? If you spin point B 90 degrees around center O, it's going to end up right there on D. This is a 90 degree angle. That's what it says here about being a square. Rotate this 90 degrees, it's going to travel, I think of it traveling kind of in an arc. Anyway, it's going to end up right at D. If I rotate A 180 degrees around O, it's going to go all the way around to here. So I kind of imagine this circle where all these points are going to kind of slide around. If you start rotating things about O, it's like things start to move in concentric circles around center sun of the universe point O. So when B went 90 degrees, it just went like this. Whoa, kind of missed there. A going 180 degrees is going to go that far along that circle. It's going to end up at D also. C is going to go positive. So let's erase all that junk. C is going to go positive. Actually, I can leave it. C, we're starting at C. We're going positive 270. You know, you could also call that negative 90 if you like that better. Those are going to be the same. But let's talk about the positive 270. Positive is this direction because it's kind of clockwise. So positive 270, I'd have to count that all the way around to here. That's going to end up at A. And if you notice, that's the same as going negative 90. Negative 90 is 90 clockwise. And from C to A clockwise is 90 degrees also. How can we get C to D? Oh, C to D. All right. We could reflect around center O. How many degrees? If we're just going to go this way from C to D, that would be positive. Yeah, that's positive 90. Or we could, once I got that that written down, all I really need to do is transform that number 90. That number 90 is, I know, the same as a rotation of negative 270. That would be around the circle clockwise, 270 degrees, 3/4 around that circle. All right, a couple more problems here, and then I'll have to end part one. Rotate triangle ABC 90 degrees clockwise, counterclockwise. I'm going to do this in red, and then I'm going to change colors. All right, A is the center, which is great. So A doesn't go anywhere, which is really nice. Oh, we're supposed to fill this out at the same time. So A stays in the same place. Lovely. Whoops, that's a 0, 0. Hard to write with this thing sometimes. Okay, and then point B. Where's point B going to go? Actually, I'm going to leave B for a second. I think C is easier to move. C, okay, so C is going to move 90 degrees around A, and it's going counterclockwise, so it's going to go this way around the clock. It's going to go like along a circular path, kind of that direction. How far does it go that direction? That's a really nice arrow, by the way. It goes 90 degrees. So right now, C is completely straight to the east of A, and if I'm going to rotate that attitude 90 degrees this way, well, I need to go a quarter of a circle around. I need to go perfectly north. And it has to maintain its distance from A because it's going to go along this circle. So C is 5 points away from A. It's going to be 5 points away from A right up here. I'll call that C prime. So C prime ends up at 0, 5. All right, and then, so I don't need that little circle thing anymore. That might just get in my way. Then also, where does B go? B has to stay this far away, so it's going to stay in a circle that's kind of 5 diagonals away, and it's going to go perpendicular. So the angle from B to A to B prime has to be 90 degrees, so it's going to be kind of off this way, and it has to be that far off. So it's actually right here. All right, I have to end part one right now. We'll come back and finish this picture in a second.